No leaning, right? Right. Okay, folks, we're doing a mic check. Can everybody in the back hear me okay? Hands up back there. Dave, thank you. Matt, okay, we can hear at the back of the room. We're good, Richard? Okay, folks, we're going to get started now. I hope everybody's got their lunch. Thanks again to Amanda and the crew here at BDSS for... Oh. Pardon that. I'm trying to concentrate. Okay, folks, we're going to get started with the afternoon agenda, so thanks again for being here. Thanks to the folks watching on the live stream. Thanks again to Amanda and the crew at the back for feeding us. I hope everybody's got a big pile of food and ready to fuel up for the afternoon. So we're going to get started with the afternoon agenda. It gives me great pleasure to spend a moment introducing an old friend of mine, a collaborator of many years, Dr. Greg Baden. As I mentioned yesterday, Dr. Baden is in Florida at the moment, so he's been kind enough to take a few minutes out of his day there to call in via Zoom so that you can get some of his years of wisdom as you embark on your solution. So a little bit about Dr. Baden. He's the chairman and chief technology officer of Penguin Automated Systems Incorporated, which is a leading research and development company that provides mobile robotic technology solutions for numerous industries. It's based in Sudbury, Ontario. Dr. Baden holds a PhD in mining engineering with a specialty in technology and economics, and is a professor, or has been a professor, at Laurentian University, where in 2001 he was awarded the prestigious Canada Research Chair in Robotics and Mine Operation. He's an international authority in the field of robotics and automation, and he's a sought-after consultant, lecturer, and speaker, and has received numerous awards and distinctions in recognition of his visionary leadership. He also holds a number of patents in mining automation systems, including robotic positioning systems for applications in open pit, underground, subsea, and space environments. So for those of you who've never heard of this before, you're going to get introduced to the concept of lunar mining, and that is literally what it sounds like, mining in outer space. As a member of Inco Limited's senior management team from 1986 to 2001, Dr. Baden was responsible for all corporate mining research. This research involved pioneering telerobotic systems within the company and globally, and included the conceptualization and implementation of the world's first robotic mine prototype at the 175 ore body. Dr. Baden was also president of Automated Mining Systems, a spin-off of Inco Limited, specializing in communications and control systems for future mine production technology. He served on many boards of directors, including the Greater Sudbury Development Corporation, Precarn Incorporated, and the Art Gallery of Sudbury, amongst others. So, ladies and gentlemen, please give a warm welcome to Dr. Greg Baden. And Greg, the mic is yours. Okay, we've lost Greg. We've lost Greg, apparently, so give us a second here. It's on his end, Nathan? Okay. Such are the joys of technology. Okay, well maybe what we should do, if this is going to be an issue, is we can bring in Greg after the panel and we can do the panel now. Okay, all of our panelists are here. Panelists on my left, are you guys ready to go now? Okay. Let's get the lights. You got the screen? Okay. Okay then, we're gonna come back to Greg when the panel's complete. We're gonna bring the screen up behind me, as you can see, and I'm gonna introduce the 5 panelists that we've got, and we'll try to get Dr. Baiden back later. So, panelists, I'm gonna ask that you remain seated until I've read all of your bios, and then come up as a group and sit on the stage here in the order that I've called you up. So, first of our panelists is Dr. Amy Prue. Dr. Prue is the professor and academic program coordinator of culinary information and food. When I read your bio and when you talked to us earlier, you were talking about the labor part. Yep, there you go, the lights are going out. Tell us a bit more about what food science is and what some of your neatest innovations. We just talked about, Nutella. People are excited by food. Michael was telling us about people's excitement about their products. What are some of the exciting things you're researching?
So food science, well, everyone is eating food, and too often we're thinking it's chefs who are preparing all of that. Anytime you walk into the grocery store, it's food science that's really the backbone of what's going on. A few of my food science students are in the room here. Wave, Carrie, wave, Michelle. It's a discipline where you're taking those culinary principles of understanding how to make food beautiful, but you're also thinking about the automation, the manufacturing processes, the food safety, chemistry, regulatory, and innovation cycles to be able to make that successful. There's so much mechanical engineering behind it, computer automation, data science, marketing, advertising, and so on that drives our food manufacturing sector. Here in Canada, food manufacturing is constantly in battle as the largest manufacturing sector in the country, back and forth with automotive. Why? Because we always eat. Mm-hmm. And when economic cycles go up and down, we are always going to eat. We may decide to defer buying a new car for a year or two, but we are always going to eat. And we're not always going to eat in restaurants. We're not always going to even eat minimally processed products. There's food science behind that too. One of the groups I was talking to, we were talking about irrigation and how many recalls were on fresh lettuce in the past couple months. Why? Because of irrigation systems. How can we impact there? Food science is a fantastic career opportunity, and it allows people to link into creative industries as well as into the technical side. And that's one reason I like it so much. One reason that I'm really excited to be here today with you is that when I was in my undergrad at Guelph, go Guelph, I'm a Niagara person, but there are many different schools that are fantastic for food studies here in the province. Sitting out at a picnic table, having a chat with one of my friends who was in biochemistry, I was in food science, and he was like, oh, we've been studying this wacky protein. And he pulls out his textbook and shows it to me. And I'm like, cool, I think this protein has some interesting implications in food and nutrition. And I'm like, do you want to work on this? Do you want to see what we can do with this? And he's like, oh no, I want to go and study parrots in Costa Rica. I took that idea that I had from a conversation, just a passing idea at lunch, went into not a hackathon, because the word didn't exist 20 odd years ago, but went into a product development competition, put my idea out there, raised $100,000 off of that experience, funded my own studies. Then the Bill and Melinda Gates Foundation picked up that same technology. That technology was spun out into the Harvest Plus program and the genetic modification of crops for improving nutrition. Now that said, lots of people say, I don't want to eat genetic modified foods. Fine. That same protein is now used in the Impossible Burger to make it bleed. If you've seen the vegan burgers that are out there, it's in one of those products. I can't begin to say how important it is to have conversations with really excited and energetic people who want to build up your ideas. I came to Niagara because, again, I had a conversation with someone at a table at a birthday party and scribbled on the back of a napkin what a food science program would look like. And since then, we've raised more than $40 million for infrastructure and for programs to bring in all sorts of great people to help food innovation happen here in Niagara. Do not underestimate the power of sitting around a table with really creative and intelligent people and then catalyzing that idea. So kudos to every one of you for being here, and kudos to the team for organizing this.
Right. That was a great point to end on. Thank you very much, Amy. And a great panel, lots of tremendous insight. I hope the audience got more thinking about how you can develop your solutions over the next 24 hours. Sadly, that brings this panel to an end. You know, one of the learnings of a thing like this is technology is great, but as we experienced 50 minutes ago, it doesn't always work exactly as designed. But we do have Dr. Baiden back online, so I'm going to thank the panel. We're going to bring the screen back down. We're going to bring Greg in from Florida. So thanks again, everybody. Okay, so we've been talking about Greg since last night. This is Greg. Greg, can you hear us? There we go, we got a wave. The microphone is all yours. Richard's just going to bring up your volume here, Greg.
Oh, okay. Hold on. There. How's that? Is that better? That better? Or worse? Hold on. Can you hear me? There you go. Thank you. So first of all, I want to thank Dave and the people there for inviting me to speak. What I did was I put together some slides of work that we've done in robotics over the years. I've been working in this field for my entire career now. Started in mining and have kind of branched out now into other areas, which I'll show you some of the mining things, but as we go, I'll show you a few more. Can everybody see that? Yeah? Okay. I started off working at a large mining company that had many of the issues that you heard the panels talking about, where we worked in underground mines, we didn't have broadband communications, and we didn't have positioning systems because GPS systems didn't work there. So I'm going to show you some of the work we've done to overcome some of those things. And I get the good fortune of explaining to you probably the better part of $300 or $400 million worth of robotics work for the mining industry and other industries. The picture you see in the center of that screen is a picture of one of our robots in the middle of a field taken from about 2 kilometers away. It's kind of the same as the Pathfinder mission, but done for industrial robots. And that group of people in the bottom are some of the team members that put together the systems that I'm going to show you. The picture that's on the screen now describes the mission of our business. It's to formulate existing and new technologies that enable the robotic operation of things to go where they shouldn't or can't. Some of those are military machines, like the ones you see in the corner. Others are machines that went deep underground to try and get scans of areas at the mines, in the mines. And you see two of the operators sitting there running the machines on the screens. We have several projects that I'm going to talk to you about for a minute. You need to realize that these projects are the result of many years of work. So one of our first projects were the two yellow robots in the upper corners. They were deployed in a mine at the top of a mountain in Chile. And the objective was to run those robots inside of the mine, where we had to build our own computer networks and have the robots drive in to collect the data that you see down below. The orange in the screens are scans of the tunnels, and those scans are then put onto the mine maps. But you see an actual rendering of the tunnel on the right-hand side, which is where where this tunnel area is able to be gathered. But the sensors the blue sensors and the other sensors up above are the data gathering system that went into the mine to be able to get those kinds of images. Those images are extremely valuable. Like you heard about in the agriculture business, things like looking at the rock for its quality and for what's in it, and being able to use the sensors to scan those things with color and density and magnetism and others help us to determine what's going on. This picture is a picture of a problem that's existed in underground mines for a long time. You see that man with a pole in the right-hand side. That's the real-life picture of him doing his job. And what he has to do is put explosives inside of all of those rocks to be able to break that blockage up. In the world today, there's 200,000 of these areas that have to be unblocked at any moment in time, and we needed a better way to do that. So our business was asked to create a robot system that would allow the operator to not be exposed in those areas. This entire machine and robot system have many innovations in them, but the key is to bring down that blockage. So in the back area of that truck is a command center with computers and joysticks and everything you need. On top of the front of the hood of the car, on top of the roof is Wi-Fi antennas to get you 2.4 and 5.6 gigabit per second radio. And on the very front is a brand new optical communication system that we patented and built in our business. On the back part of the robot, or the back part of the truck, is a charging system for special batteries that allow that robot to run for 12 hours with a 1-hour charge cycle. And then the robot, which you see down below, has a special communication system on it, as well as special robot arms that can reach out, drill holes into the rock and place explosives without anybody having to go there. This is what that robot kind of looks like in animation deployed, so that we drill a hole in the large rock to break it up. I'm gonna try and see if my video works, Nathan, over this link, and you can tell me if it works well or not. But this is a video of how that process has to work. The machine has to drive in and deploy the robot. And once the robot gets into the tunnel, then it would be there for a fairly lengthy period, and the main command center would come back and run that robot optically out into the area where the blast zone is. When you're blasting underground, you have to make sure that people are safe. And you also need the situational awareness for the robot to be able to deploy itself and get out into the area. These kinds of specialized robot arms are very difficult to build because they have to fit inside an opening that's only 3 meters high. And so you have to have special extensions and things to be able to figure out where to put the drill hole and then align it, drill a hole, and then blast it. Once those rocks come down, then the whole production cycle is able to be restarted again because the blockage is gone. And you'll see the blast in just a second. This is a different view of the same thing, but it shows how the sensing system we have on board is trying to pick different rocks at different levels to be able to put the robot arm to and load the explosives. This is one of the areas where we use specialty imaging and special scanning systems to allow the robots to pick where they are and where they should go to. You see the red robot is deploying itself to match where the purple robot is. And once it gets into the right position, then it can go and do its job. This video shows you that the kind of robots we build are not really like Rumbas. These are very large machines of several tons. In fact, they're more like robotic tanks. The robots have to be able to turn on a dime because they're like a turret on a tank to be able to get those robot arms in place. And the operator has to use the cameras and all the sensing systems to be able to operate them successfully. When that robot arm is fully deployed, it's 15 feet out from the robot and 30 feet high with an end effector that can drill a hole, load explosives, and or special explosive charges to bring down those hang-ups. That's just one of the kinds of robots that we build. And it's interesting that a lot of the base and the robot arms are going to be refit for the agriculture business as we move into the future. We build several different kinds of robots. They range from a 60-inch diameter robot to go into sewer tunnels, which I heard spoken about. The sewer tunnels need to be able to not only have the robots deployed, but they need to scan them for what they look like inside and be able to take samples of the water, the gray water that they're in. We also have a 2-ton machine, and you just saw the 6-ton machine, but all use exactly the same control systems to be able to do their work. I want to tell you about a different technology that we had to put in place, which is a cooperative robotic system. In this bench up here, there was 200,000 kilograms of explosives at 300 kilograms of explosives per hole. One of the holes went off prematurely, and we got called in a safety perspective to try and dismantle this pattern. The idea, which you see here on the left, was to build a containerized system with these 3 robots. And when we were finished, this was the portable command center and the robots that were built. We get into things that have very tight timelines, and so this entire system had to go from idea to solution in less than 20 weeks and be deployed. When we did our work, you can see there's the robot that I showed you in the original picture driving out, and it had to drive out almost 3 kilometers to get to site from our command center. And you see all the robots here in our command center taken from the robot looking back. Oops. And we had to try and determine the temperature of the holes that you see up here. There were 575 holes that had to be monitored for temperature, and then these robots would have to dismantle the explosives from them. The last little bit I'm going to talk about is, well, I've been in the mining business. We've been working on the next generation of mining for space. Probably about 15 years ago, I wrote a strategic plan for the Canadian Space Agency on how to mine the moon. And so this slide is for a new business we have called Moonrise. And the idea is to build teleoperated lunar mining equipment that's run from Earth on up in space. These kinds of machines you see in the corner and these kinds of robots for making oxygen and bringing it back to low Earth orbit are the kinds of future mining that are going to take place. As well, we have to make rail cars that are going to have to work in space, and these are some of the fuel delivery vehicles that we had looked at how we would deploy them and operate them using the same robotics technology that we're all talking about today. And these are some of the space techniques for how to bring those rail cars back to Earth. One of the very important things from a friend of mine, Dr. Bill Stone, is to build a space brake and get that, to get those rail cars back. And then once they're there, we have to process the water to be able to make it rocket fuel. The reason we would do all that is because today, to bring water from Earth to low Earth orbit, which is where our satellites are, would cost $10,000 a kilo. But to do it from the moon back to low Earth orbit is only $500 per kilo. And so there's a huge future in economic development of space for mining once we have the kinds of robotics technologies we need. So with that, I'll try and have, as best I can, a conversation with you guys. But that's the team of people that have been working on that. And I want to thank you for your attention. Okay.
Okay. Greg, thanks very much for being with us. Great. If Nathan we logged off from Greg now? We've logged off. Okay. So it was great of Greg to be here. Again, thanks. Several of the panelists are still here, so thanks again to them. It is now about 8 minutes after 1. So we managed to get everybody fed and get some more insight and wisdom about the industry in almost on schedule. So for the rest of the day, you're going to continue to work in your teams on your solutions. One other small public service announcement that I will make is several of the teams have asked for some clarification about the presentation formats and rules for tomorrow. So shortly we'll be delivering a sheet of paper to all of the tables to just outline the judging criteria, the formats, the time limits, and the overall format of the pitch competition that will start at 12:30 tomorrow. So the lights are coming back up, and you can go on back to work. And thank you very much.